Okay, welcome back guys. We're going to be solving the question 6 from the first chapter of the Johnston textbook, Mechanics of Materials. And in this question we have these two brass rods AB and BC with uniform diameter that are braced together at point B to form a non-uniform rod of total length of 100 meters that will be suspended from a support at point A. As we can see, we know that the density of the brass is 8470 kilogram per meter cube, and in the A part of the question we need to determine the length of rod AB for which the maximum normal stress in ABC is minimum, and the B part we have to determine the corresponding value of the maximum normal stress. So the two conditions that we have in here, in order to have the minimum maximum normal stress in these two, so what we have in the free body diagram is that first of all we have the weight of these two. We can call this the weight of AB, and we have also the weight of the rod BC. And the givens that we have in this question is that, so we have the diameter of each of them, which is going to help us to find the area for each. So all the diameters are known. We know the density of the brass is 8470 kilogram per meter cube, and the way that we're going to use this is that we know that rho, or density, is equal to mass divided by the volume, and we know if we want to find the weight we will have mass times acceleration of gravity. So basically for finding the mass we'll have density times the volume, and since we have cylindrical rods, the volume would be simply the area times the length of the rod, which we're going to show it with L. So we know, so from here, mass is equal to W over G, and for the density for our volume, we're going to put A, which is area times the length, and from here we can find the weight. Basically rho times G times A times L, and again G would be the acceleration of gravity, 9.81 meter per square second. So that's the use of the density in this question. So with density we're going to find the weight of each of these two bars. Actually we can start with that. So if you want to find the weight of AB, we'll have rho, which is 8470 times 9.81, and for these two we need the area. So for finding the areas it's pretty easy. So if you want to find the area of AB, we have pi divided by 4 times the diameter of AB squared. So if we calculate this, we have pi divided by 4, and if we look at the AB part, we'll see that the diameter is 15 millimeter. So 15, we're going to divide it by 1000 to get it in meter squared, and this is going to give us 176.7 times 10 to the minus 6 meter squared. So the weight would be basically, we're gonna plug in the A in the previous part to find the weight, 176.7 times 10 to the minus 6, and the L in here would be the length of the AB, which we know is A. So that was for the AB. Let's do the same thing for BC. So for finding the BC, again we have the same thing, same density times 9.81 times, let's figure out the area for BC. So pi divided by 4 times, this time we have the diameter of BC. Let's see what we have in the figure. So the diameter is 10, so pi divided by 4 times 10. Again we're going to divide it by 1000 to get it in meter, and if we calculate this we're going to get 78.54 times 10 to the minus 6 meters squared, and we're gonna plug it in here. So 78.54 times the length of the BC, which would be simply B, and we know B would be 100 minus L. So in here we have A plus B is equal to 100, so basically our B is 100 minus A. So we're just going to put this in here, 600 minus A. And the reason I'm doing this is that when we have, so we are trying to, based on the A part of the question, what we are trying to figure out is the length of AB. So basically we have to figure out the distance of A in order to have the normal stress of ABC minimum. And that's going to happen when we have the maximum normal stress of AB equal to BC, because when we have these two equal, we won't have any stress difference and stress shielding between these two. So that's the condition that we're going to figure out the A. That's why in here I'm writing B based on A, because ultimately we're going to use that. But that's not the whole story. The whole story, we have to go with the free body diagram of each of these two. Let's start with the free body diagram of A, and the force that we have, we can call it P AB in here, and we have two different weight of AB and weight of BC. So if we do some of the all forces in Y direction, obviously there is no force in X, equals 0. Since we are in a static condition, we have PAB minus WAB plus WBC equals 0. So PAB would be basically WAB plus WBC. So we already found these two, and as long as we have PAB, we know that the normal stress in AB would be basically PAB divided by A. And so all of these are known. We just have to figure out the PAB, which would be simply WAB plus WBC. So from here, what we can find for WAB is, so here, if we calculate this amount for WAB, we get 14.68 times A. And for this part, if we find the WBC, what we're gonna get is 652.59 minus 6.526A. Now we just have to plug those two to find our PA in here, which was WAB plus WBC. So what we're gonna get in here is that 14.68A plus 652.59 minus 6.50, and if we calculate this, PAB will be 652.59 plus 8.157A. And from here we can find our maximum normal stress, which is PAB. So basically we have 652.59 plus 8.157A over the area which we found at the beginning of the question. So what we have in here, 176.7 times 10 to the minus 6, and this is gonna give us 3.69 times 10 to the 6 plus 46.16 times 10 to the 3A. So that's what we have for AB. So we have to do the same thing for BC too, but we'll have a different free body diagram for BC. So BC, we have PBC in here, and we only have the weight of BC. Obviously, the force that we have in AB is greater than BC. So in order to have this stress minimum, this has to be again equal to each other. So PBC, this one again, we're gonna do sum of all forces in Y direction. This will be positive. PBC minus WBC is equal to 0. So PBC is basically equal to the weight. So in the previous part, we found the WBC, which was, we can go back, what we found in here, 652.59 minus 6.526A. And if we want to find the maximum normal stress, we have PBC over ABC. So again, 652.59 minus 6.526A over what we found for the ABC, which was what we found in here, 78.54, and this is gonna give us 8.31 times 10 to the 6 minus 83.09 times 10 to the 3A, and that's gonna be the second part that we were looking for. all we need to do in here is just to put the stress in AB is equal to BC, and in this condition we're going to find the maximum normal stress minimum, which is what the A part of the question is asking. So basically for the A, this is what we found in here. I'm just going to write it down in here. 3.69 is equal to 8.31 10 to the 6 minus 83.09 A, and what we're going to get in here is 4.62 minus 129.25 is equal to 0, and from here we can find A, which will be 35.71 meter. So that's what we're trying to figure out in the A part of the question, and in the B part we just have to find the maximum normal stress in this condition. So we can go either with maximum normal stress in AB or BC. Really doesn't matter. Let's go with the BC, which is easier. We have a shorter formula for BC. So I'm going to do 8.31 minus 83.09 times 10 to the 3, and A would be 35.71, and here we're gonna find 5.34 times 10 to the 6 Pascal, or 5.34 megapascal for the maximum normal stress in AB or BC. So yeah, that would be all for this question. Hope you guys find this one helpful. Please let me know if you have any questions. I'd be happy to answer those in the comment section. You guys take care, and I'll see you in the next video. Have a good one.